It's my pleasure to introduce Dr. John Sullivan and Dr. Laura Judd, who were both co-PIs on the TRACER AQ campaign, which they'll be talking about today, which happened last summer. And this is a NASA DOE collaborative field campaign. So John is in the atmospheric chemistry and dynamic lab at NASA Goddard. He's also the head lead of NASA, the Tropospheric Ozone Lidar Network. So he has a lot of expertise and background in taking measurements using remote sensing, such as LiDAR, for applications in satellite validation, air quality, stratospheric trends, and so forth. Before joining Goddard, he was actually at MPP. And as you read in his bio, he has a lot of experience with field campaigns other than Tracer AQ, such as Outlets, Discover AQ, Chorus AQ, and so forth. And also talking today is Laura Judd, who is a research scientist at NASA Langley Research Center. She also dedicates parts of her time as an associate program manager for Health and Air Quality Applications Program up there at headquarters. She has a lot of experience with air quality, policy, regulations, and so forth. And before she joined NASA in 2016, she got her bachelor's degree from the University of Nebraska and her PhD from the University of Houston. She has a lot of experience with remote sensing of NO2 and formaldehyde, a lot of work with GCAS geotasm. I'm sure you've seen her name in a lot of publications, presentations using that data. And along with being a co-PI with John, she was also a co-PI in TRACER AQ. And with that, I will hand it over to you all.
Thanks, Matthew. I'm going to share my screen. I'm assuming you all can see full screen mode?
Full screen now, yes.
Looks good.
Great. So I'll go ahead and kick us off. John and I are going to be swapping back and forth, and we welcome any questions, especially if there's clarifications that are needed along the way. So feel free to interrupt us. We're both pretty casual. So we titled this talk "Connections to Geostationary Air Quality Observations During TRACER AQ," which we'll get into what TRACER AQ was in detail in a little bit. But this was it's a field campaign that happened in Houston, Texas last September. And thinking about connections to geostationary air quality. For those of you who aren't familiar with what's going on in the air quality satellite world, there's being a lot of changes over the next few years, with adding at least 3 geostationary sensors operating over some of the most populated areas of the Northern Hemisphere. So GEMS launched in February 2020. Tempo will follow early next year, followed by Sentinel-4 in early 2024. And so a little bit more about Tempo. It stands for Tropospheric Emissions, Monitoring of Pollution. I hope a lot of you on the call have already heard about it, but if you haven't, it will be located in geostationary orbit, measuring high spectral resolution UV visible light. From that, we can retrieve parameters such as NO2 and formaldehyde, as well as tropospheric ozone, and even trying to distinguish ozone within the boundary layer. The PI for this mission is Kelly Chance from Smithsonian Astrophysical Observatory. The project's managed by NASA Langley Research Center, and the instrument was built by Ball Aerospace and is expected to launch, I believe, in January of next year. So as you can see from the animation, it'll scan during most of its time across larger North America every hour throughout the daytime, capturing the diurnal evolution of this pollution that hasn't really been seen from the satellite perspective before, as sensors in the past have been in low Earth orbit, largely capturing the early afternoon, some morning perspectives as well. So as alluded to from our introductions from Matt, John and I have been involved in a lot of these airborne studies the last 5, 6, 7, lots of years. And this is just a compilation of air quality studies that have involved at least the airborne remote sensors components from over the last decade. So this started with Discovery Q in 2011 through 2014, and then there was a lot of these other studies, some larger headquarters directed studies such as Chorus AQ and FireX AQ, and then some smaller, more collaborative studies such as Outlets or Listos. And so you can see that each number represents a different study that has happened, and we've covered a wide variety of areas across the country, and actually a lot of commonality that you'll hear about today is that a lot of these are in urban coastal areas. And so there's a lot of complicated dynamics that goes with having these being near water bodies with sea and land breezes, and the stability of layers, the complexities of the boundary layer.
So I will jump in here and introduce TRACER AQ. I'm John Sullivan, by the way, and thank you, Matt, for the introduction. Laura and I had really started thinking about air quality campaigns that we wanted to sort of explore using some of the additional measurements that we've sort of developed at NASA over the last few years. And really, we got lucky in a sense that the DOE TRACER study led by Mike Jensen, and we can provide additional details on that study and links and websites for that study as needed. But the original idea was really to have a full-blown DOE-funded TRACER study, and then coincident with that, an AQ extension of that, an air quality extension of that, overlapping in September of 2021. And as everyone knows, the last 2 years has been complicated for planning and logistics, so the TRACER campaign actually was pushed back, and they are actually in their measurement period right now, with the intensive period being in summer of 2022. So TRACER AQ really is sort of now in a lot of ways was able to use and leverage the DOE existing measurements on the ground. So we really want to just acknowledge the fact that a lot of this, at least in the initial planning, and I'll mention some of the forecasting a little later, really was leveraged off the back of DOE. And I also wanted to mention TCEQ also did a lot of heavy lifting on this campaign. So TRACER AQ, the NASA-led air quality portion of this, and our partners, and Laura and I, as I mentioned, we started developing the campaign, the white paper, and we wanted to really break down the study into three, major focus areas, and that is sort of better understanding ozone photochemistry as it relates to local meteorology. So these are some of the bay breeze or sea breeze cases that Laura described, and how that recirculation might impact or degrade air quality in a certain region. Houston is sort of notorious for these types of events. Modeling and satellite evaluations. So how can we really use these observations to both evaluate existing models, push existing models, potentially some of those models that may be the a priori for the Tempo satellite or other satellite platforms, and also evaluate existing satellite products such as the once daily or twice daily Tropomi overpass or something on that order. And then the third, which I think I have to thank Laura and a little more of her focus on the applied sciences route and really trying to understand the intersection of air quality and socioeconomic factors. And this was a bit of a learning curve for me. I hadn't quite really gotten into this focus area before, but it is really interesting. And we'll show a slide or two at the end on how I think this campaign and these observations really do a fantastic job of linking the airborne measurements and the surface measurements to then connecting that to socioeconomic data. Next slide, Laura. And I will get to this map and all the details in it over the next few slides. So September of 2021 was the campaign study. You may recognize the map in the upper right-hand corner here. This is the last 10 years, or this type of map, but this is really the last 10 years of AQI values for Harris County, Texas. These are AQI values, so yellow, these are code yellows, code orange, code red. You can see in the details there, the associated details in that. What I want you to notice, or what I want you to take away from this is Houston has a bit of a bimodal air quality seasonality to it. So you do see some of these elevated ozone or elevated pollution episodes in the early or late spring, early summer, sort of April, May, June. You have a bit of a lull, and then you pick back up with some of the higher ozone or higher pollution episodes in late summer, early fall. That's really driven in part by synoptic meteorology, just either being more favorable to having the pressure systems available for higher ozone and ozone production, or you just get a synoptic system in the middle of the summer in some ways that ends up being more moist and a lot wetter and not as productive for ozone production. Some of that coming off of the Gulf as well. The bottom panel here, just I'm trying to just walk you through maybe some of the strategy we took in designing the campaign, and this leads into the siting of the equipment. But you really want to better understand, and especially when working with the state agency TCEQ in Houston, how we design the measurement strategy. Really, we want to make it policy relevant science. So one of the first steps is to take the existing monitoring sites in the Houston area and try to understand which ones are consistently measuring higher pollution values, which ones might really benefit from additional enhanced monitoring. So that's exactly what we did. And what we show here is the Aldine site was the design value for the region when we developed the campaign. So we added additional measurements there. We didn't, followed by some of the other monitors as well. And we can get into more of this a little bit offline, but just trying to better understand, better link our measurements to the regulatory community is really part of this effort. Okay, so I put this slide together because I know we had a little more time, just some snapshots from the field. The diagrams don't do it justice sometimes. I like to show figures like this. Just starting from the left is we had a pontoon boat that really was able to transect the Galveston Bay, so that body of water due east of Houston, which gets a lot of the outflow from Houston, a lot of that urban outflow, but also sets up some of the interesting meteorological cases. So it's really an interesting sort of body of water and atmospheric chemistry experiment as its own. And we really wanted to push to get some measurements over the water. So we worked with the University of Houston. This was largely led by Jimmy Flynn and Travis Griggs at UH. But outfitting this pontoon boat with an inlet to get overwater sampling of some of the trace gases, a salometer to understand that boundary layer difference between over water and over land, and then NASA Pandora. The top middle there is the Red Eagle, which is a research vessel that was able to, or actually a boat that was able to go out into the Gulf, big enough to go out into the Gulf on several days during the campaign. And we're actually able to launch ozone sondes. I did mention this, we were also able to launch ozone sondes on the pontoon boat as well, and ozone sondes on the Red Eagle, as well as some additional equipment on the Red Eagle for trace gas sensing. On the upper right there is ozone sondes. This is taken from the LaPorte site, and credit should be given to Paul Walter there in the red shirt, who led a lot of the ozone sonde prepping, and sort of he was just the ringleader when it came to where we launch, who to call, all of the metadata, and it's been incredible. And all that data is in the archive already if there's anyone that has interest in that. Moving to the middle panel here, we just wanted to show that we had some drone activity at the University of Houston site, mostly with just a small ozone monitor in-house. There, either a home-built ozone monitor or a POM 2B ozone sensor, co-located with the NASA Pandora instrument. The mobile lab there in the middle, courtesy of University of Houston. This is what you might see referred to in this talk as MACL-1. And really a lot of trace gas measurements there in the back of the pickup, actually in the bed. If you walked around that trailer and opened it up, or that truck and opened it up, you'd see essentially rack-mounted analyzers all throughout the back of that, and actually that mast in the front measures and can sample, I think, 10 meters above the ground. So sort of an atmospheric chemistry lab on wheels, if you will. Moving to the bottom panel here, the TOLNET picture, not as exciting, but a large trailer that houses an ozone lidar, which I'll show you some more data throughout the talk today, as well as AeroNet and MPLNet equipment throughout the campaign domain, and the aircraft utilizes the NASA G5. I think if you squint, you can see Laura in the red and myself in the gray, right to the right of the letter v, the V. But it gives you a scale of the size of the G5 if you haven't seen it. And Laura can probably provide more of the stats later on in terms of altitude and speed and all those things if you're interested in that. But and not pictured was the GMAO and forecast support team. So really to pull something like this off in the middle of COVID, right before the Omicron spike, but still when Delta was going really bad, was just quite a challenge. And you know, I just hope that you take into consideration what you're seeing here. It's all preliminary. We're working on final data, but I will be quiet now and move on to some more interesting slides, which is exactly this. So this is just a pictorial diagram of the campaign, setting up just to orient you a little more in terms of Houston. The major sites you'll see throughout this talk, you'll see Aldine in sort of north of Houston, University of Houston in the center. You might not see it, but Sugar Land is due west of Houston. To the east of Houston is LaPorte, which is one of the major TOLNET sites. Galveston Bay there, represented by the boat over the water. And then you'll see the Red Eagle out over the water. So and once again, kudos to the regulatory agency TCEQ. All of the yellow dots there were some of their existing ozone. In addition to, I think those might just be ozone monitoring sites, but many of those sites have additional trace gases as well that we'll be using for additional analysis. Next slide.
All right. I think next we just wanted to take a deeper dive on a few of these assets before we start showing some data. So thanks John for introducing about the G5. I'm gonna start by telling you a little bit about the two instruments that were on board. So you might have heard the name GCAS thrown around. So GCAS stands for the GEOCAPE Airborne Simulator. So if you remember the GeoCape mission study from the first decadal survey, this was the airborne component of that, and there's it's primarily been used during these airborne campaigns to prepare for geostationary observations, so getting to the spatial resolution as well as the temporal resolution that we're going to get. And so there's an example that shows an animation of the LA Basin, which is still my favorite data set that I've collected personally to date. Capturing the sea breeze front kind of moving through the basin, which was, I thought, kind of neat. And so our two primary products are really NO2 and formaldehyde. NO2 is pretty mature. Formaldehyde's starting to mature and make its way into some research applications. So this instrument measures similar to a satellite, so we're measuring high spectral resolution, UV visible, and actually into the near infrared light. There is an ocean color channel of GCAS. So it observes from the belly of aircrafts from which it is installed that have these remote sensing portals on there. So its field of view as we're mapping, so its swath width is about 7 kilometers. We flew at 28,000 feet, so it's a 45-degree angle. So you can do the geometry to figure out if we flew higher, how that would change. And we flying these parallel lines spaced apart so that we have a little bit of overlap, so we can collect kind of a gapless map and really get an aerial representation of what's happening over the hours that we collect. And it's been a part of a lot of various missions, as I showed earlier. So that was on the G5, and this is the first time that we've actually put these air quality remote sensors on the NASA G5, which is really exciting. So along with that, GCAS flew with HSRL-2. This wasn't necessarily a new combination of instruments. This is a payload that was flown during Discovery Q, is those instruments together. So, but what was new is that HSRL-2 had a dial channel for ozone profiling. And this was the first time that it was demonstrated actually during a science campaign. It was demonstrated during demonstration flights, but this is the first time it's been deployed for science on the HSRL-2 instrument. So it's a nadir pointing multi-wavelength LiDAR system. And you can get data products such as aerosol backscatter, depolarization, extinction, AOD. From that, there's different retrievals where you can get mixed layer height, which can be really helpful for data analysis and classification of aerosols. So we flew on the G5. There's a couple pictures there showing the G5 on pre-flight, some of the most beautiful mornings out there on the tarmac at Ellington. And then you can see what one subset of our team on one of our flight days on the aircraft. So there's each day we flew about 9 hours. If we flew a full flight, it was about 9 to 9.5 hours. This allowed us to map 3 times over the area represented by the brighter colors on the left, the greens to the reds, which shows the sampling density during I wanted to call it Discover AQ, Tracer AQ, sorry. And so really one of the beauties with this sampling strategy is we were able to collect 27 maps over the same domain over the course of the month, ranging from clean to polluted scenes. And so we're going to really have a lot of data to work out some statistics as to what we're seeing over this area. As shared before, the Pandora spectrometers were also an important component of TRACER AQ. If you're not familiar with Pandora, you can think of it as a ground-based satellite looking up at the sun or measuring in a max DOAS fashion, doing scattered light DOAS. Its operational products are NO2 total column, ozone total column, and as well as profiling with the max DOAS. And then something new, more on the research side, but is available for use, is formaldehyde. So we're really excited to have that addition during this campaign. So in Houston during Discover AQ or Tracer AQ, I don't know how many times I'm going to do that today. We had 9 Pandora instruments, courtesy of the NASA Pandora project at Goddard, as well as Elena Lynn at Virginia Tech. And so these were spread out at 4 stationary sites. 3 of the stationary sites had doubled up Pandoras. So one was more optimized for doing more direct sun DOAS, which means which has a higher accuracy and better precision than ground or than a max DOAS scattered light profiling. And then there were actually 2 mobile Pandoras, one on Mackle 1, the mobile lab, the truck that you saw earlier, and then one on the pontoon boat. So we can get some kind of spatial analysis going on there. And then the plot on the right just shows a single day's worth of data of direct sun total column NO2. And I just put it in here just to highlight the dynamic differences between these different areas of Houston. I know that the labels mean probably nothing to you all relative to what's going on in Houston, but there's a lot of variation going on, which we will show in a little bit. And then actually for a deeper dive, I'm told that Pandora is going to be talking to this group or giving this seminar in about a month. So I encourage you all to go check that out to see more Tracer AQ data as well as Pandora data in general. I'll pass it to John.
Sure, thanks, Laura. I think if you have a minute, 2 comments in the chat. Well, one from Laura Arachi, woot, Geotaza, so thank you, Laura. I guess that's more of a comment. And then Sam, thanks for your question, Sam. Good to see you again. What kind of NO2 column resolution accuracy are you getting from GCAS? But an easy answer or something to go later?
No, that's a good question. So so the spatial resolution on the G5 is something on the order of 250 meters by 350 meters, I believe. I got to take a closer look at it. I did the math. back in Tracer AQ, so 6 months ago. So it's a little bit coarser than what we got in the King Air, just because our ground speeds are 50% faster. With that, we can get our spectral fits for NO2 are on the order of, I think it's like 8 times 10 to the 14. So it's pretty good. It's comparable to what you get from tropomi at the higher spatial resolution. Formaldehyde, I'd have to get back to you on that. Air mass factor uncertainties are going to be same orders of magnitude as satellites, which are typically about 30 to 50%. But I will say that during the previous campaign, I haven't done the analysis for Tracer AQ yet because I'm actually just now starting retrievals. But during Listos, which was the last campaign that GCAS flew on, that we have data for, it compared against Pandora within plus or minus 25%. So it did really well, and it had no systematic bias that we could see when comparing to those data sets. So hopefully that answers your question, and happy to kind of dive deeper into it later on as well.
Cool, thanks, Laura. So I wanted to just throw a slide in here to remind folks TOLNET while I had just a little bit more time. This is really and I'm leading up to this because there were 2 of these instruments deployed to Tracer AQ for this campaign, but they've also been deployed for many of the other campaigns that Laura mentioned, and there's future campaign plans as well. So really what these deployable ozone lidars, some of them are deployable. Generally, they're able to be in the field for a 30-day period to support something like the aircraft flights that Laura just mentioned. So you can imagine how sort of excited I was when we found out that we'd also have the dial profiles from the aircraft. So now you have really this 3-dimensional picture of the TOLNET lidars at select sort of anchor ground sites who are able to measure not 24/7 all the time, but during select periods 24/7. So you have sort of these anchor points of continuous ozone profiling, and then raster maps from the G5 of ozone profiling. So really understanding both the spatial and temporal evolution, and then the aircraft was able to fly at night, but the lidars were able to operate nocturnally. So then you also start to be able to sort of probe at some of these questions of daytime dynamics versus nocturnal dynamics. So really exciting data set, and I'm really pushing, I think, the science team to get some interesting papers out of this. But all that being said, the network goals really of TOLNET, this is, although I am based out of NASA Goddard, there are 8 or 9 institutions affiliated with TOLNET. On the bottom right is actually the network map that we have that I think I borrowed from Matthew many years ago. And the site and institution, I should have added another column there of associated members of the group, or sort of those individual PIs. But I can drop some names in the literature or the website, and you can also grab that information there. Really what we try to do is provide ozone profiles throughout the PBL and into the free troposphere. Each of the ozone lidars are different. They're all homebrew. So really, some of them are able to measure really high fidelity ozone in the PBL, but might not be able to capture the UTLS, but they may be transportable, whereas others are sort of fixed long-term measuring sites, like I've shown here at the Table Mountain site on the upper right corner there, where you actually have the ability to measure routinely at high resolution into the free troposphere. And there's a nice paper written up by Fernando and Terry at JPL on some of the measurements they saw and comparing it to the WRF-Chem measurements. And since Matthew Johnson is hosting this, I thought it was appropriate to put in the next slide. You want to go? And one of the really key components of the TOLNET system or TOLNET framework that I think has really benefited from our collaborations, our continued collaborations with Matthew, is understanding the ability to get these targeted forecast air quality alert systems. I don't know how much he's talked about this with you guys at the lab level, but it's sort of this interesting combination of grabbing model data or having it pushed to him, however you want to think about it, but using that information to essentially think about how best to put a ozone forecast alert to each of the TOLNET sites. So we're sort of fundamentally now network-wide observing sort of in syncopation, and that had been many years where we weren't doing that, and there'd be an event, a pollution event or a stratospheric intrusion event, and we just weren't really thinking on that sort of network, CONUS US tempo-like scale. And now I really think that this forecast alert system has been a really interesting component of all this to pull the measurements together. So I want to just highlight this forecast system in action. An interesting case that happened in Boulder where the ozone lidar there in Boulder, this is Andy Langford and Chris Senf and Raul Alvarez, who you may know. Essentially, they get a forecast for a stratospheric intrusion into the lower free troposphere. That is a request for them to turn on the lidar and begin operating the ozone lidar there, Topaz, based out of NOAA and NOAA CSL. And in turn, their measurements indicate higher levels of ozone. They actually have a good working relationship with their local state agencies, CDPHE, and they demonstrate that the ozone levels they're measuring might actually be unhealthy for certain groups that are actually living at some of the higher elevations in the foothills and above. So it's sort of an interesting example I find, and I've taken this slide up to headquarters, and folks like Barry Leffler and Jack Hay love this type of slide where it's really showing some policy relevant science that's sort of breaking the it's breaking through a lot of different communities. So kudos to Matthew for doing this and continuing that work. And I put this slide in here as well because the thinking about the forecast in this mode actually, I think, allowed some of the measurements for TRACER-AQ to adopt some of those forecast features moving into the framework of the campaign. Here is what you might call the scorecard for the campaign, in the sense that this is really every day, so the month of September, broken down, sort of matrixed by platform. Blue indicating here that the measurements were operational, and a number, for instance, sun is the number of launches, or rasters, number of rasters of the G5. I don't know if Laura hit home the point hard enough, or I may have missed her. I want to reiterate that, the G5, the raster we developed, the flight planning that we developed, it really was to try to get 3 full raster patterns if we could. And that was really to begin to understand that variability temporally that we're hopefully going to be able to see from tempo. But a lot of these questions that went into this, the ground speed, the vertical resolution, so the spatial resolution, things like that, we really, one of our main thrusts of this, we really wanted to make sure we could understand that temporal variability. So we had to obviously make some considerations for that to meet that end goal. But what I want to say from the broader perspective, the top two rows here are ozone AQI and PM 2.5 AQI. And we did have a nice code red event. I say nice because we'd like to see something to measure, but not always great for the folks of Houston for their air quality. But on September 8th, we had a code red event, and you can see it was a multi-day event. We actually, shortly thereafter, get Hurricane Nicholas to come and greet us in the Houston region, which set things down for a little bit for a few days, especially as you can imagine, that pontoon boat that I showed you was not able to remain on Galveston Bay when the hurricane arrived. So we had to, of course, put that in, we had to put that in boarding before, and then after we were able to get back out. And we actually sort of worked out well because there was some time where we had all the science team and staying nearby in the hotel, and we began sort of talking about, what remaining science goals do we have for the campaign? What on our scorecard do we still want to get? What in those research focus areas have we not really approached yet? And I think we ended up getting a second sort of air quality event towards the end of the campaign, and we were able to really kind of better understand the air quality there. So I think that's all I want to say for this slide. Just reiterate that the blue are measurements on that panel. So from Laura and I's perspective, from going into this you know, this is essentially something that never happens with a campaign. I mean, you basically almost had 100% duty cycle for everything in the field and on the aircraft. I mean, it was just, it was really incredible. And all the logistics planning, you know, all of the direct and indirect hurdles we had to go over was incredible. So I really just couldn't be happier with the amount of data collected and how I think we're now starting to kind of see some of that in action. So I think Laura and I have chosen the next few slides are sort of just some simple highlights of some of the measurements we saw that we think might be interest of this group. And of course, those are sort of paired with different focus areas. So just to reiterate them, you can see them on the screen here. And that, there you go, exactly what I just said. The following highlights that. So here was a day where we had forecasted a high ozone in the Houston area, a little bit south of the Houston city area, but also high ozone over the water. So this was a perfect day to really try to explore this ozone photochemistry and meteorology. And ozone is forecasted over the water in elevated levels quite frequently, and there's really a historical lack of observations of this ozone over the water. It's rare. It's mostly in campaign or sort of experimental or research mode only. So when we saw this, we knew we really wanted to put things in place to try to better observe that ozone over the water. So this was a day where we had the Red Eagle. That was the ship I showed earlier in one of the snapshots. And Paul Walter on the ship as well. And we were able to release an ozone sonde incredibly well timed as well. We released the ozone sonde basically right when the G5 was, not right when it was there, but in close proximity within several minutes. And what is really interesting to me, and I think really exemplifies how challenging this problem can be in terms of understanding air quality over the water is you do see ozone at the surface being upwards of 100 to 110 part per billion. But it's in such a shallow layer. Your box is squished down to the point where all of your photochemistry is happening in a 500-meter box. So you can really get very high levels of ozone. And I assume other constituents as well. This was just largely targeting ozone. So you worry, or from a regulatory perspective, to kind of bring this home into the broader impact is if you now have so we've done the observations to quantify the ozone over the water. Now you begin as a regulator or someone in the public health community to wonder, you know, if there is a recirculation of that air mass and that comes back on shore, how is that really going to affect the public? And I can show you a little bit more on the next slide. I think how we were able to probe these measurements with the LiDAR measurements. So taking a step back, I'm realizing now this is a busier slide than I intended it to be. But what you're seeing here are two essentially almost week-long ozone LiDAR measurements. So this is an ozone LiDAR at the LaPorte site in Houston, which was very near the Galveston Bay. So you think a little bit east of Houston proper, but near enough to the water that you do get some of the dynamics, localized dynamics that you might get associated with a recirculation or a bay breeze or a sea breeze. And really and I should say that I'm going to focus on the top panel here is associated with sort of the longer measurement period. September 8th was the code red day we were referring to, and you can see a bit of a buildup there. Yeah, so actually, if I had a blown up portion of this curtain, and that might have been a little better, you can actually see we do get high ozone at the LaPorte site, but it is not until several hours later than what you might expect as sort of your canonical high ozone that you might get in the afternoon. It really wasn't until 6 or 7 p.m. that this sort of polluted air mass made it to LaPorte. And it was well mixed enough that you have to sort of understand the dynamics to think about it, but it's a pretty strong evidence, in my opinion, that it's a recirculation effect getting back to the LaPorte site. And we see this several times throughout the time series in the front. Of course, we hope to work with some of our high resolution models that we hope to have some analysis on this later down the line to better understand some of this. But the observations are really, at this point, pretty phenomenal in my opinion. And then the bottom, we won't focus so much on this during the rest of the slides, but just I did kind of toot my own horn in that we had such a long measurement time series. We broke our record in the top panel. The hurricane came through, broke our record for continuous observations. The hurricane came through and we made some adjustments, and then we actually broke our record the second half of the campaign for longest measurements. So we are excited to share these. And I think that if this is something you're interested in or looking at, I think of all of the data sets that I've been able to provide from the ozone lidar at this site, this is probably one of the best data sets we've ever collected. So really exciting. So I will, I think, pass it to Laura now. Oh, no, I won't. I mentioned we were working with some modelers to compare some of the ozone lidar data. This is a very quick comparison just simply of the September 8th day, just trying to better understand both some of the ozone origin and how the model might help us better understand ozone mixing down from aloft versus ozone transported from another region into Houston and things like that. So I expect there to be some really interesting ozone modeling, observation, analysis, comparison papers in the future. I think we are really, we have some interesting questions that I really think are kind of ripe for some quick publications. So I won't comment on this too much longer, except that it's in the works. So.
All right. Thanks, John. And I think I'll wrap us up with a few more slides, probably 5 minutes or so, to show some airborne data and how that links to modeling and satellite evaluation. So this is showing preliminary data from GCAS on the top. You have NO2 and formaldehyde, and what a lot of you may not have seen before is the HSRL2 ozone data. And what this is showing, I would say, like boundary layer ozone average. It's the average concentration that the LiDAR retrieved in the lowest 1.5 kilometers. And so you see this morning, midday, and then afternoon showing the diurnal evolution of that ozone production and its movement to the south with the weak northerly wind that we had. And so what I don't show here too is that there's the aerosol adjacent data set that goes along with that as well. And so we see this as being a nice data set where that can be used to evaluate models, but then also contribute to tropomy evaluation, as well as use it to prepare for what we're going to see from tempo. We've been talking with, we talked earlier this week with Aaron Nager on using some of this data to see if we can create some tempo proxy data and kind of take a deeper dive look at the spatial resolution of tempo versus what we get from the high resolution data. Which I think I got ahead of myself because this is kind of what shows it at the preliminary, but this kind of shows the best case example where you bin data to what we expect from tempo. So you can see that there's still going to be a lot of spatial information preserved, but what's not shown here is the inherent noise structure that tempo will have as it's not adding a couple hundred pixels together to create a pixel. And then just hitting into the final focus area, where a lot of this was motivated by a paper that was done by, led by Angelique Dematillo from University of Virginia, where she used GCAS data from Discover AQ to look at NO2 disparities specifically in Houston. And this is where she found that NO2 was 37% higher for non-whites and Hispanics that live in low-income neighborhoods compared to whites living in high-income tracts. She has since expanded this to tropomi data, showing that a lot of this can be attributed to diesel trucks, vehicles, diesel exhaust. And she and her team at UVA, along with her advisor, Sally Posede, plan to look at this data from TRACER AQ to both update the analysis from 2013 as well as think ahead about the temporal evolution from morning to midday to afternoon, and also connections to formaldehyde and ozone, since we have those data sets as well. So we're really excited to make that connection. And if you guys haven't read any of these papers, I highly recommend them. They're very well written. It's very nice analysis. I would just Google Dematillo NO2 and you'll probably find them. Or I can put links in the chat if anybody wants to ask. One last shout out highlight from TRACER AQ was educational outreach efforts that was led by Brenna Biggs. I think this is her first field campaign in her new role at NSERC, and she really knocked it out of the park. I think like 2 or 3 weeks before the campaign, we were planning on doing these in-person visits, but COVID Delta made that impossible. I mean, there were questions as to, I mean, people were coming to us like, are we going to the field and everything? And we went to the field. Nobody got sick. I would say we were very, very lucky that and I mean, we took all the precautions, but you never know with that many people in the field. But Brenna actually took it in stride and transitioned everything to virtual in a 2-week time period. And in that, she did over a dozen presentations. She almost reached 100 schools, almost 3,000 students. And she was able to get the scientists involved as well by getting us on to MTS while we were sampling, and they were able to ask us questions, not all related to air quality, but it was a lot of fun. And just a huge shout out to her and the success there in us wanting to kind of, I guess, inspire the next generation or let them know the cool things that we're doing and why air quality matters. And then, so just looking ahead at one final slide, and we're at 10 to the hour, so this is good timing. Just looking ahead beyond TRACER AQ. So John and I mean, we're ready to dive into TRACER AQ data. We're not forgetting about it, but we're also looking ahead to future opportunities. And our next opportunity is in 2023. And it is related to Tempo. Tempo is expected to launch in 2023. And so we're planning to get the same assets that we did during TRACER AQ out in the field in a few different areas of the country. So this mission's called STACS, Synergistic Tempo Air Quality Science, where it really seeks to accelerate tempo science soon after launch. And by collecting these enhanced data sets with the aircraft, with TOLNET, with Pandora. And this is in collaboration and really a lot of leveraging of other activities that are happening fortuitously in 2023. So there's the NOAA Roma campaign. So the G5 is going to deploy with the NASA DC-8, where the DC-8 will have an in situ payload measuring air quality in our primary targets are Los Angeles and New York City, and then we're looking at targeting some other cities as well. And then there's some other, I would say the majority of the activity is happening in New York City at that time period. And so I just wanted to get it out there that we're starting to get the wheels going on this. We do have a website, and I realized I didn't put it on this slide. Maybe John put it in the chat. But that is our final slide. And so, John, do you have anything to add?
No, I've been trying to add comments in the chat as well. I think I've got some of the links up there that folks might be interested in. But I think, you know, in terms of the slide here in front, we are excited to basically, TRACER AQ is a bit of a dress rehearsal in some respects for doing this campaign in New York, well, in multiple cities with some ground emphasis on New York City. But doing it when tempo is in the air is kind of exciting. So tempo will be measuring all the time in all of these cities once it's up, which I don't know if Laura mentioned. I think they're targeting a January of 23 launch date, which I think is still pretty firm. But I encourage anyone who is interested in tempo, but they haven't quite dug into information about it. I mean, there are workshops, there's early adopter workshops, there's synthetic tempo data. If you want to, just get your hands on some of the data, format, et cetera, to be able to ingest the data once it arrives. I don't know if we even let off with that the tempo is expected to provide not just hourly retrievals of NO2, but also one of the products that is going to be really important for some of the validation efforts is a 0 to 2 kilometer ozone product. So you can sort of understand, both Laura and I, the assets that we've brought into the field are really trying to help both evaluate the geostationary platform sensors and also hopefully add to some of the kind of remaining questions in air pollution science and atmospheric chemistry. And I think with that I've got no other questions. I did see a chat. Aaron Dooley helped us out with NTS. I remember he did some demonstrations, and I was blanking on if he actually added on any images or graphics. And you want to comment on that? I thought we ingested either some additional radar data or model data that he had really helped us with. But yeah, kudos to Aaron and that whole team. It was a fantastic resource for real-time flying, and in fact, I mean, having someone on the ground connecting, using the XChat or something like that, having that MTS especially with the radar or some other sort of synthetic radar loops is really a powerful tool in real-time flight planning. And it's probably safe to say that some of the flights would have ended quite differently had we not had it, in terms of where the aircraft would have gone. So.
Okay, well, I would like to thank Laura and John. This is a great talk, the overview of this, and just the amount of data that's going to be coming out of this field campaign is quite amazing. I wish I had two of me to kind of work on more of this, because it makes you so excited to see all this. And I'd like to give an extra thanks for coming on, the first day of March Madness, and well, I forget what the holidays they were.